Lesson 5.4 has us dealing with special systems of linear equations. Now, hopefully you remember when we say special solutions, we mean two very specific things. At least two that we've dealt with so far. All real numbers, or infinite solutions, and then no solution. Okay? So there's two situations where these things happen. So if I'm on a graph, the special solutions happen when the lines either always cross or never cross. Now, one of those hopefully is obvious for us. What does it look like when two lines never cross? Well, those are parallel lines. Parallel lines are going to cause no solution. But we have another way of figuring out that they're going to have no solution using algebra. So parallel lines mean no solution. And then we've got another situation similar to parallel lines, but they're actually stacked on top of each other. So this blue line and this red line are the same line, which means they're intersecting at every point. So the same exact line is going to give us all real numbers. Now, what I mean by all real numbers is that there's an infinite number of points. So all of the x values and all of the y values are options for ordered pairs. Infinite solutions is probably more appropriate here, because it's not every combination of ordered pairs. There's just an infinite number of them, and every x and y value has a solution. So we've got all real numbers, no solution. Those are our special solutions. Solve the system. All right. There's two ways I want to look at this. One way is the math expert view, is I see two equations that have the same slope and different y-intercepts. And I want to be able to say, based on what I know from chapter 4, that they're parallel and I should get no solution. Circle that. That's my answer. Okay, that is an option when it's noticeable and recognizable for you. But I need you to tell me they're parallel to say no solution. The way I'd expect most of us to do this is by using our substitution method. Y equals 2x plus 1. So I'm going to substitute that in for this y. And now I have the equation 2x plus 1 equals 2x minus 5. All right, there's nothing to distribute, so these parentheses don't need to be there. Now let's try to solve this. As soon as I try and subtract 2x to get them on the same side, they both cancel. 0 plus 1 is 1. 0 minus 5 is negative 5. And we run into this situation where the variables cancel out. Remember that. The variables cancel out. And we compare what's left over. Does 1 equal negative 5? No. No solution. What this means is we were not able to find an x value. And if we can't find an x value, we can't get an ordered pair. There is not going to be an ordered pair that solves this system because they're parallel. These would be two lines going like this with the same slope that would never cross each other, parallel lines. Another system to solve. This time I look like I'm set up for elimination, so I'm going to do the elimination method. I'm going to double the first equation to get my numbers to match up. It's going to bring me down here with negative 4x plus 2y equals 6 from distributing. Well, now what the heck? These are the same exact equation. Well, same equation is going to give me infinite solutions. This can be a stopping point for us. But if we continue on down, we'll find the algebra way of making that decision. All right, we want these to cancel, so I'm going to subtract. -4 minus -4 is 0x. 2 minus 2 is 0y. 6 minus 6 is 0. Those cancel out. 0 times x plus 0 times y. Well, that's just 0 equals 0. All right, this means that there's always going to be a solution for x, which means that no matter what x I plug in, I'll find an ordered pair that works. That can only happen when the lines are on top of each other. This should look familiar from chapter 1 as well. Infinite solutions. All right, so this is a situation where the numbers ended up equal. So similar thought process to chapter 1 when we were learning about this is that when the variables cancel out, and they cancel completely, we get a special solution. That's the same concept as chapter 1 when we were doing this just for single equations. It comes back, it works the same way. When the variables completely cancel out and we're just left with numbers, we're going to end up with one of our special solutions. Finally, we've got a modeling problem, a word problem. And what they give us is two shapes where all of the sides are based on variables. All right. So the idea here is, remember when we discussed two missing variables? If we have two data points, we should be able to solve them. This is an exception to that rule. We'll describe why it's an exception once we have an answer. So perimeter just means adding up all the sides. So this means 2x plus 4x plus 6y plus 6y. Those are all four sides. Should add up to 48 kilometers. Combine like terms, that's 6x plus 12y equals 48. For the rectangle, 9x plus 9x plus 18y plus 18y. That's all four sides added together, equals 144 kilometers. Combine like terms, that's 18x plus 36y. All right, now let's line these up and solve. So I'm aligning this one up down here. This is essentially where I'm starting my solving the system thing. I got two equations from the perimeter. Add up all four sides, it equals the perimeter number. Now we've got two equations. This looks like it's set up for elimination because all the variables and the equal signs are lined up. But I need to multiply the bottom equation by 3 to get the numbers to match to cancel out. 3 times 6 is 18. 3 times 12 is 36. 48 times 3 is 144. This is a situation where the equations end up being exactly the same. There are infinite solutions, but that doesn't really help us because we didn't find one solution. Okay, so let's explain why this didn't work. In math, those two data points to be able to figure out the x and y values have to be unique. If one of them is an exact multiple of the other, like what ended up happening here, even though these were two different shapes, what the equations came out to, the rectangle was exactly 3 times as big as the trapezoid in every way. The x values, the y values, and the perimeter, when I actually had it written out in an equation form, it was exactly 3 times as much to get to the rectangle. So in math, we wouldn't actually consider that a unique data point. It doesn't give us any extra information because it's just a scaled up or scaled down version of the same thing. Okay, so you need to choose different numbers, different ratios of your data points. So for example, if I were trying to figure out how much things at Taco Bell cost without actually checking the menu, if I got 2 beefy 5 layers and 1 drink, and my friend got 4 beefy 5 layers and 2 drinks, those are not unique data points. got exactly twice as much as me, so you should spend exactly twice as much money, and this can't help us figure anything out. What would need to happen is get a different number of one of the items. So it's a different ratio. So I don't know what the relationship between these is going to be now. But because they're unique data points that aren't perfectly scaled up, I'd be able to figure out how much a BF5 layer and how much a drink costs. Okay, so these are unique data points because they're not perfectly scaled up. This trapezoid in this rectangle, the trapezoid was exactly 3 times as big in every way when we looked at the variables. That is not a unique data point. Try to understand what I'm talking about here. All right, this is where you can demonstrate you really understand what's going on. All right, up until now, it's just been copying the exact process I give you. Understanding this relationship and why it happens will help you understand a little bit deeper kind of the purpose of solving systems. All right, that's it for 5.4.